Okay, so the major point of this lecture is going to be going over a few alkene and alkyne reactions that sort of build towards synthesis. So what we've been looking at so far are reactions where we could look at the mechanism and see what happens in regards to getting the product. There's more reactions that are useful in terms of creating molecules, but in which the mechanism is usually either too complicated or, well, not worth going over. So those are sort of reactions where you do sort of just need to memorize the reagents and the process that happens. So the three for the alkene reactions that I kind of glossed over are these three right here. Suppose you start with an alkene like this, just a regular double bond in the middle of the molecule right there. Let's look at these three reactions. So the first one up top is called hydrogenation. And as you might have guessed, the point of hydrogenation is to add hydrogens across the double bond. So again, first one over here, hydrogenation. It's usually done with some sort of a catalyst, usually platinum, maybe nickel, sometimes doped palladium and carbon. So the transformation that occurs is the addition of those hydrogens across the double bond, and it would look something like this. Note the most important part in remembering this mechanism, well, sorry, not this mechanism, this reaction, is that the addition is syn. So we were talking about anti before. Anti means the things that are added across the double bond are on the opposite side of the molecule. Syn just means the opposite. It means that both the things that were added are on the same side of the molecule. So in this case, they both added on dashes, but they also could have added on wedges. The other two we're actually going to go over as well also have, well, one of them has syn addition, the other one doesn't really matter, I guess. So this one on the bottom right is called dihydroxylation, also known as syndiol formation. So an alcohol, well, it gets the -ol suffix, and if you have two alcohols that are adjacent to each other, we usually call that a diol. So in this case, the syndiol formation, or the dihydroxylation, takes place with this osmium tetroxide through a very strange sort of intermediate, and then you use water and peroxide as an oxidizing agent. So again, for these sort of reactions, we don't really care about the mechanism so much. If your professor wants you to know the mechanism or the transition state, you should learn those, but really the important ones for alkenes are the bridgehead intermediate and the carbocation intermediate. Okay, so again, this is also a so-called syn addition, which means both of these OH groups added to the same side across the double bond, and again, they both could have been dashes. Okay, the last one over here is the use of MCPBA, and we'll learn more about that much later in the course, perhaps in organic chemistry too, but this reaction is called epoxide formation. And it won't be so useful until later in the course when we start learning about how we could actually do reactions on epoxides. But we'll just sort of introduce it here. So what happens is that basically you get an oxygen attached to both sides of the double bond, just like this. And this is called an epoxide. Okay, there's not much more to know than that. Sometimes these will be synthetically useful. We'll talk about that later when we actually start doing synthesis problems. So the rest of this is sort of focused on getting you familiar with the common alkene reactions that you'll need to know for your exam. Okay, so I've given you a central molecule here, and then we perform these kinds of reactions on it. So this is essentially testing you if you remember the reagents, and some of these will have mechanisms that are important for you to arrive at the right product. So take 5 or 10 minutes and attempt these. Pause the video now. Okay, I'm going to assume you tried it on your own. Let's look at what each of these turn out to be. So up at this top left corner, you'll see over here with the Br2 and the H2O, this is what we called our halohydrin reaction. You form a bridge with the Br2. And then in the second step, once we have this bridge here, if you could imagine it, it gets attacked on the other side by, well, the water, which is a relatively good nucleophile. So the result is you get anti over here. Technically, if I want to be more correct, I should put this methyl group on a wedge because it got pushed up by the water while it added. Okay, so again, bridge formed by Br, H2O comes in and attacks from the other side. You get this and the enantiomer. Okay, what about this over here? If you remember this, we called this our Alkoxymercuration reaction. We also form a bridge with the mercury. The THF, if you remember, is just the solvent. And the H2O, just like in the halohydrin reaction, is the nucleophile. Afterwards, we use the sodium borohydride, the NaBH4, to do the reduction. So what you have is the OH adding to the more substituted side of the double bond. This is a secondary carbon, and this is a tertiary carbon, so we'll add here. And you could also get the wedge as well. So you'll get a pair of enantiomers formed in equal proportions, so it'll be a racemic mixture at the end. Okay, let's look at this down here since I introduced it briefly up there. Here, in the previous reaction, we had the platinum being our catalyst, but here it is the nickel. That doesn't actually change anything about what happens, so let's look at what happens. Okay, your final product will be this. So remember, the hydrogenation reaction adds the H's across the double bond, but remember they both need to be added on the same side. So you would have an H over here on a wedge and an H over here on a wedge. What that does is it forces this methyl group to come out on a dash. Now if your H is added both on the dash side, then your methyl will be pushed up to the wedge. That's why you also get the enantiomer that comes from that. Lastly, we have, well, I guess I should again put the name on this one, hydrogenation. Over here we have what we called earlier the halogenation reaction. So we have some HX and we have a solvent that doesn't really play a role, and we're going to proceed through a carbocation intermediate, which means that when we're adding onto this double bond, we could either get a positive charge here or a positive charge here. Because of the hyperconjugation effect, we expect the positive charge to develop on this tertiary carbocation that's more stable than the secondary. But if you look over here on the adjacent carbon, this is also tertiary. It does have a hydrogen that's invisible attached here. So in the initial step of the electrophilic attack, you will form a carbocation here that's tertiary, but this will also be tertiary. What that results in is, because those are equal in stability, is that you'll get a mixture of products. So a hydride shift could still occur because these are equally stable, and you'll get this. And remember, because you have a sp2 hybridized carbon, when you're in the carbocation intermediate, the Cl can add to either side, wedge or dash, so you'll get a pair of enantiomers. What I'm really trying to hammer home here is that whenever you proceed through a carbocation intermediate, you don't get good selectivity. So when we're going for a total synthesis, when we're going for building a molecule from a series of reactions, one of the things you want is to maximize your yields and to maximize your selectivity. That is why we develop reactions like oxymercuration, or if you remember hydroboration, because those are selective reactions. You don't get as much of a mixture of products. Okay, let's look at another series of potential reactions. So again, these should be familiar to you. Give these a try for 5 or 10 minutes. Pause the video, and then we'll try them. Okay, I'm going to assume that you tried to work through these reactions. So at the top right, we are going to have the Hydroboration reaction. If you remember the hydroboration, it adds an alcohol across a double bond to the less substituted carbon. So wait a sec while I get that. So you have the choice of adding the alcohol to the secondary or tertiary, but because we're forming the anti-Markovnikov product, the H will add to the more substituted side, and the OH will add to the less substituted side. Again, that was because of the electronegativity difference between the H and the B in the borane molecule here. And of course, you also need to remember that because of that square planar intermediate, the hydroboration is a syn addition, which means the H and OH will be on the same side. Again, that pushes this over here to a well, whatever this isn't, so if these are going to be wedges, this gets pushed to a dash. And what happens is you get a pair of enantiomers, again, that are going to be formed in approximately equal proportion, so it's basically racemic. Let's look at this. So you saw this earlier. It was one of the new reactions I introduced you to. It is the epoxide formation. So it is simply going to look like this. Okay, at the top left, we have the bromination, or just in general, the halogenation reaction. So let me write that in. This is halogenation. Remember, halogenation proceeds through a bridge intermediate, which means that the Br first adds here and forms a bridge, and then the second Br, as a nucleophile, wants to attack the more substituted carbon. The reason is because that carbon will have the partial positive charge. So the nucleophile typically will attack the partial positive charge, which will be at this location. Because the bridge forms in one direction, perhaps say in the wedge direction, you know that the other Br must go underneath and attack, so these two Brs will be trans or anti in the final product. What that does is it pushes this methyl group that was already here onto the same side as this Br. So once again, as a result, you will get a pair of racemic enantiomers. Okay, now let's look at this mess that's occurring over here. So if you realize it, the sulfuric acid you could just treat as hydronium ion, and this is the hydroboration reaction, which will proceed through a carbocation intermediate. So in the initial step of the electrophilic attack, the H will be attacked by the nucleophilic double bond, and the positive charge will initially form at that location there. So let's draw the carbocation intermediate for that. Okay, so you're initially going to get this, which is tertiary, but if you look to the right, this is a secondary carbon. If you look to the left, this is also a tertiary carbon. So what is possible is that you could get a carbocation rearrangement through a hydride shift to this position here. Now, those of you that remember our ring expansion reactions will also note that because the double bond was in the allylic position, it was located here, and you generated a carbocation one substituent or one spot off the ring, you are setting yourself up for a ring expansion. Hopefully you remember how to do that. If you don't, be sure to watch one of the old videos, but the general procedure is you look at this ring here, and you look at the substituent, and you try to find out where it ends. So here it ends at 8. We go backwards 7, 6, and then choose either side 5, 4, 3, 2, 1. The reason you want to do that is because it makes it easier if you number it in such a way that in the ring expansion 1 will attach to 6 or 4 will attach to 5, whatever will attach to whatever without skipping a number. So what I mean by that is your ring has 6, 1 to 6 connecting makes sense, 4 to 5 connecting makes sense, 3 to 4 connecting makes sense, but if you number it in such a way that, say, 2 and 4 connect, then you'll still arrive at the right answer, but it'll be more confusing for you or yourself and whoever else is trying to follow your work. So that said, you'll get this, but again, this is a secondary carbon, and this is a little quaternary carbon over here, so there's no hydrogens available, but there is a methyl that's available. So what you could get is a methyl shift to this location, which will give you this tertiary carbocation. So the moral of the story is if you follow through each of these, you'll get this attack here by the Cl, you will get this attack here by the Cl, and of course you're going to get enantiomers generated in each of these, but I'm going to omit that for now. Don't forget it though, you'll get a Cl adding here, and you'll get a Cl adding here. So let's compare these. If you look at this one, this is tertiary with 5-membered ring. This is tertiary with a 5-membered ring. This is secondary with a 6-membered ring, and this is tertiary with a 6-membered ring. So if you remember, 5-membered rings and 4-membered rings typically have ring strain. So the 6-membered rings have less ring strain. Those are actually pretty favorable. In addition, you know from the hyperconjugation that tertiary carbocations are more stable than secondary carbocations. So the only thing you know is that of these 4, this will be your major product because this is the most stable. It has the tertiary carbocation in a 6-membered ring. That is the most thermodynamically stable. However, this is what I guess people new to organic chemistry fail to understand, is that that does not mean that this is going to be super selective. In other words, this is your major product. This is the thermodynamically most stable one. However, the energy difference between any of these 3 or any of these 4 is not that great. They're actually pretty similar in energy. What that means is that if you performed this reaction and you were trying to get this product, you would get it in major proportions, but you don't know the extent. So if you had these 4, maybe you'd get this in 26%, maybe you'd get this in 22%, we don't know. But the moral of the story is that this is going to be your major product, but remember there's 4 possible things you could generate. So you don't know the extent to which this is going to be favored. Maybe this is in 99%, maybe it's in 26%. It is the major product, but there is a possibility that these side reactions will still occur. So if you're trying to make a synthesis, remember you're doing the reaction, and then once the reaction is done, you try to purify your product. So if you have these 3 other guys that are present in your reaction mixture at the end, it is very difficult to separate them out and arrive at the pure version of this. So really, when we're talking about synthesis, when we're talking about selectivity, you want to choose something that doesn't proceed through a carbocation intermediate, because again, we don't want rearrangements to happen. So halogenations are good, hydrobarations are good. Anything that goes through a carbocation intermediate that isn't very selective is bad for your synthesis, because while this will be the major product, you will have these guys probably hanging around. Okay, so hopefully that clarified some of that. Okay, let's look at yet another series of reactions. So take 5-10 minutes, look at these, and pause the video. Okay, I'm going to assume you gave those a try. Let's first look at the top right one. So this is again our Alkoxymercuration, but you'll notice that we're doing it in methanol instead of water. So this is actually what's called Alkoxymercuration. And the key difference is that instead of the water doing the nucleophilic attack, the methanol will do the nucleophilic attack instead. So instead of adding the OH to the more substituted side of the double bond, which is this, you'll end up adding the methanol to the more substituted side, and the O on the methanol will be the nucleophile here. So this will be your product, and of course the enantiomer. Over on the bottom right, this was the dihydroxylation reaction I was talking about earlier. So again, you have to be careful with these syn additions. You know the OH will add the same side, but that pushes this other group, this methyl group, downwards. So you get a pair of enantiomers. In particular, when you have these 4 or 5-membered rings, you might be asked a question that deals with chirality. You always want to be careful about the existence of a potential meso compound. I won't go into that too much here, but always be on the lookout. Don't forget the basics from the first part of the course. Okay, in the bottom left, we have what I have called the haloether reaction. Instead of the halohydrin reaction, where water does the nucleophilic attack, the methanol will do the nucleophilic attack instead. So the bridge will form over here, and the more substituted carbon will be attacked, which will generate that, and of course the enantiomer. And lastly, instead of the hydration with the alcohol, we're doing the hydration reaction with methanol here. So your methanol will attack once the carbocation intermediate is formed, because these are symmetric. We don't really need to care about the potential for rearrangements. So that's what I mean by caring about that carbocation intermediate. So this is a good example where you can use a carbocation intermediate in your synthesis because it is selective. Because even if you get a rearrangement, at the end of the day, you're still going to get an identical product through that rearrangement. Okay, so the other thing you learned were alkyne reactions. So there are two alkyne reactions that are super important that I didn't go over, and those are the two hydrogenation reactions. So both of these are hydrogenation of alkynes. So the first one is H2 in the presence of Lindlar's catalyst, which is a very special doped catalyst that will, upon hydrogenation, give you the cis-alkene. The other one, this NaNH3, will give you the trans-alkene. Again, these aren't too interesting since we don't go through the mechanism, so I just say remember what these transformations do and be able to use them in synthesis. Okay, so take 5 or 10 minutes and try this problem. Okay, let's take a look. So you should have seen all these reactions in a prior video. Let's start at the top left. So this is the hydroboration reaction for alkynes, which will add the carbonyl to the left substituted side of the triple bond. You really don't have to worry about that when you have a terminal triple bond. So this location here, the carbonyl will add and you'll get the aldehyde. On the other side, we have the oxymercuration of alkynes. So your two choices, the more substituted carbon and the less substituted carbon, this one will add here in the oxymercuration reaction. Over here, we have the excess halogenation, which simply means that your halogen will add across the double bond or triple bond twice. Here, these should be BRs because I was doing it in BR2, but really there's no big difference. You could either make it Cl2, so this will be correct, or you could slash out each of these and make them BR. I think you understand the overall point. Then we have this geminal hydrogenation reaction. You have to remember the key point of this is that it's relatively selective, even though it's a carbocation intermediate, because the first Cl will add and it will stabilize the carbocation that is formed there during the second addition. Because of that stabilized carbocation, the second Cl will add to the same spot, and we call that geminal. So if they're on the same carbon, that's geminal, and it's still a hydrohalogenation reaction. So it's the geminal hydrohalogenation. Lastly, this super important one over here is one of the most important for your synthetic uses. It allows you to elongate your carbon chain. So remember, with the base, the NaNH2 in solution, the sodium cap will come off, and you'll have the NH2 as a base, which will pull off this H and put the lone pair here on the sp hybridized carbon right here. So that's a pretty good nucleophile, which will attack at this carbon here, breaking the bond to the Cl. Remember, Cl is a pretty good leaving group because it is the conjugate base of a strong acid. So you'll get this here, which has more carbons than this. Okay, so now you should know essentially all the main reactions for this unit for the second exam. So this is the beginning of our road to synthesis. So I'm going to tell you that these reactions are essentially all the ones you already know, but this basically allows you to relate the functional groups together. It allows you to see the transformations between one functional group and another. So this is what we call a synthesis web. I recommend you make one for each of your exams. So pause the video here and try to write in the reagents that you need for these transformations. And now, hopefully, since you have all of these, if you actually paused the video and went through them, try the second half of the web over here. So pause the video once more. Okay, I'm going to assume you gave this a try yourself. Let's fill in the web. So the first one over here on the left is the dihydroxylation reaction we were looking at before. Over here on the top left is the epoxide formation using MCPBA. Down here on the bottom is something you might be unfamiliar with. This is ozonolysis with the oxidative workup. On the bottom right over here, this is again an ozonolysis reaction with dimethyl sulfide being your reductive workup. Over here, this should be a super familiar reaction to you if you've been doing practice problems. It is the halogenation reaction, which you've seen many times. Okay. Now over here, this one's a little bit new. It's the elimination reaction we looked at in the alkynes video. It is an internal elimination reaction, so we only need 2 equivalents of the NaNH2 base. If it was terminal, you would need 3 equivalents, and you need to add the water afterwards to reprotonate the alkyne product. Going back over to from this alkyne to the trans alkene, you would need to use NaNH3. Now over here, going to the haloalkane in the bottom, you would need excess halogenation over here in the top left. That requires the use of a carbocation intermediate, but it is selective. This is the geminal hydrohalogenation reaction. Over here we're going from alkyne to cis alkene. So if you remember from earlier in this video, you need to use the doped Lindlar's catalyst to get there. Next up, going from the cis alkene to this over here is the halohydrin reaction. On the bottom, going from the alkene to the alkane is just your regular hydrogenation reaction. We're getting toward the end of the diagram now. Going from here to the alkyl halide with an ether is the haloether formation. Going here through a carbocation intermediate from the alkene to the alkyl halide. This one's okay once again because you're going through a carbocation intermediate that is on a symmetric molecule, so you will have selectivity in your product. Is the hydrohalogenation. Going from the alkyl halide to a longer carbon chain, this is probably the trickiest one because you're used to seeing it in the other form. This is the base catalyzed SN2 reaction where this acetylene is deprotonated by the NaNH2. It attacks here, and then we need to use the water just to make sure that this carbon over here is reprotonated once more. This you could ignore. I believe it's the exact same as the general hydrohalogenation reaction as before. On the bottom left here, this is the oxymercuration of alkynes to give the carbonyl on the more substituted carbon. On the bottom right over here, this is the hydroboration of an alkyne to give the carbonyl on the less substituted carbon. Once again, over here, we need to use either Lindlar's catalyst or NaNH3 to get our alkyne to an alkene. Then finally, we have oxymercuration of an alkene to give an alcohol on the more substituted carbon. We have Alkoxymercuration to add an alcohol across the double bond to make an ether. And then lastly, we have hydroboration of an alkene to give an alcohol on the less substituted carbon. So this is the completed web. I recommend, again, for every exam you make some sort of web like this so you know how things are related, and make sure you know all these reactions for your second exam.